which we have looked at rational functions before, or you've looked at rational functions before. In Algebra 2, we spent a whole chapter in this, both in honors and in regular. So we've seen rational functions before. So today is going to kind of quick review on a lot of the things we've seen. There might be a little bit that's new, but not tons. Yes, sir?
For the quiz on Friday, is it over 4.3 and 4.4?
4.3 and 4.4. There will be no rationals on the quiz. Like, that is not a part of it. This is 4.5. This is separate part. So it'll be like the Descartes, the finding all possibles. It will not be a 5th degree like we did yesterday, guaranteed 100%. I will not have you do one of those on like a quiz or a test that take too dang on long. I was gonna say I don't have one with copies made right now. I can get you one if you'd like. If you want to swing back by later. Yeah, I can print one out. Because I know Miss Blaze has one.
No.
So I can, if you want to swing back by after lunch, I can have some reviews if you want to practice it more. It would just be more of like what we did yesterday. Awesome.
And did you start it or start from scratch? You have it. That was my question.
As what the last
I said I forgot. No, it's not. Oh, don't worry about this. This, like,
you can, if you want to sit back there, if you want to sit any of this.
I got really mad. And then Justin wasn't helping.
Yeah, if you turn them in, like probably leave. I'll take them. All right, so rational functions, they've put them in together here with our polynomials because it's really when we have two polynomials in quotient. So instead of multiplying them together, we're dividing them. So they are related to our polynomials. They just kind of do all the rest of things differently because they're special. So most of the time, we're going to talk about polynomials that look like this when they're in what we call our quotient form, which is where I just have two pieces that are in fractions that look like this. I'll show you what it looks like when it's in a different form. But for the most part, what we're going to do is put them in quotient form to do what we need to do. The first thing we're going to be asked to do with our polynomials, or with our rational functions, is to find the domain. And our domain for these, we found domains for fraction-based equations before, but we're not going to have any square roots on here. So we're never going to have that it has to be greater than 0 or less than 0 for these kinds of statements. Our numerator is always going to be a function like a quadratic or a linear, where its domain goes from negative infinity to positive infinity. So the only place we're going to have problems is where our domain equals 0, or where our denominator equals 0. So to find our domain, the first thing we need to figure out is when does our denominator equal 0? So I'm going to look at my denominator, my x squared. Hello, why are we not writing on screen? Super fun. Love that. Oh my gosh. Yay. No, that's not what I wanted. Fine, I'll do it this way. Grumpy computer. So we want to find when our denominator equals 0. So I'm going to take my x squared plus 8x plus 15. And I want to know when that equals 0. So what are we going to do for that? How do I figure out when x equals 0? Factor it. When we're dealing with rational functions, we are going to wind up factoring so many times. I do not care how you factor. If you use a box, if you split the middle, if you do bottoms up, if you factor by grouping, whatever. I don't care how you factor. Just that you factor correctly. So what is our factored form of x squared plus 8x plus 15? 5 and 3. Our pair of numbers multiplies to make 15, adds to be 8. So we'd have a positive 5 and a positive 3. So you can factor when our a value is just 1 by just doing the x frame part. Multiplies to be 15, adds to be 8, positive 5, positive 3. So what are the two solutions here? X equals -5, and x equals -3. Those are the two places where my domain equals 0. So those are my two problem children. Those are the two things that need to be kicked out of our domain. So we can do anything from -infinity to +infinity except -5 and -3. So our domain will be from -infinity to -5 and from -5 to -3 and from -3 to infinity. We just have to kick out the -5 and the -3. So we just put them in with our parentheses and jump over them. Because anytime we have a 0 in the denominator is when we have a problem in our domain. It might be a discontinuity, it might be a hole, it might be an asymptote, it might be something that causes us problems, but it's going to mess with our domain. So anytime we have a 0 in the denominator, we have a problem in the domain. Questions on that bit? Okay. Because my computer's in a mood, I'm not going to be able to go back to pages with writing, so I'm going to double check before it changes. I can save it so that I can upload it, but I can't go back to it because my computer's in a mood. Yes,
So
Julie?
we don't do anything with the range.
We will only catch range like once we have an image, because calculating range without an image is obnoxiously pedantic, and it's so much easier if we can see the dang thing. So we will only do range once we actually can see it, which we'll do tomorrow and Monday. Okay, anybody need more time on this page? Okay. So the next thing we're going to look at is intercepts. So we are going to find x-intercepts and we're going to find y-intercepts. On the left-hand side here, we have another rational function, very much like the one we saw in the very first page, in that quotient form. This is what our other kinds of equations are going to look like, and this one's called transformation form. When we have something in transformation form, we will change it into quotient form, and I will show you how to do that here in just a second. We're going to start with our quotient form when we're looking at these intercepts. Quotient form. So when we're looking for our x-intercepts, we want the zeros of the numerator. Because if we think about x-intercept, that's when we have some number for our x, but our y is going to be 0. So if I want my y to be 0, my answer to be 0, that means my numerator has to be 0. 0 over anything is 0. So to find our x-intercepts, we find the zeros of the numerator. So let's do that first. So if we look at this f of x here, we want to find for our x-intercepts, which I'm going to put x int because I am lazy. I want to take my numerator, that x squared minus 2x minus 8, and I want to know its solutions. When does that thing equal 0? So again, we're going to factor. If I need a pair of numbers that multiplies to make -8 and adds to make -2, what are we going to have? Super close. -4 and a +2. So be really careful. It is very, very, very important that we factor correctly. It is more important that we factor right than that we factor fast. It is super important. We are going to have so much factoring in this. It is a lot. If we have an a value of 1, we can take our shortcut from the x frame where I know we're going to have our x with the -4 and our x with the +2, giving us our factors. If we have an a value that's not 1, we need to use some sort of tool to help us with our factoring, because we keep forgetting about that a value. Just saying. So what are our solutions for this quadratic here? Yep, so we're going to have our positive 4 as a solution here and our negative 2. That gives me the x values of my x-intercepts. Do not tell me our x-intercept is x equals 4. That's a line. Our x-intercept is at the point 4, 0. Because we are going to wind up with asymptotes on these equations, these functions, that will be written as x equals 4 or x equals negative 2, and they're lines. So we're going to have a mix of both points and lines as answers. So make sure if your answer is a point, write it as a point. If your answer is a line, write it as a line. So our x-intercepts are 4, 0 and negative 2, 0. That's these guys. Our y-intercepts, if we think about the y-intercept as a point, that's always when x equals 0 and we have a y value. Like, that's what it means to have a y-intercept. So what we can do is, I know my x is going to be 0. We can substitute in 0 for x. That second half where it says the ratio of the constants, I'll show you what I mean by that here in just a second. We're going to do it with substituting in 0 first. So for our y-intercept, we're going to take our function and we're going to substitute 0 in for every single x. So for my numerator, we're going to have our 0 squared, which is 0, minus 2 times 0, which is 0, minus 8. And we're going to have in our denominator 0 squared, which is 0, plus 2 times 0, which is 0, minus 15. So you can do that by just straight up substituting in 0 for x. I just kind of simplified a little as I went. What do we get when we simplify this a little bit more? 8 over 15. We get, technically we get negative 8 over negative 15, but the negatives cancel out. So we get 8 over 15. That little phrase at the end of our kind of definition at the top where it says the ratio of the constants, what that's pointing out to us is if I look at my equation up here, and we look down here at the end, our constants that have no x's with them, I get negative 8 over negative 15, which is exactly the same thing as 8/15. So you don't have to substitute in 0. It is going to be the ratio of our constants. Make sure we're careful about signs. But our y-intercept is going to be the point 0, 8/15, which admittedly is going to be an obnoxious point if we ever have to plot that. But we could do it. So that's our y-intercept as a point right here. Questions on this left one? This one on the right is in a different form. It is not the same as our quotient form. This one's in what we call transformation form. And honestly, this is the way we did a lot of our graphing when it came to Algebra 2. Transformation. Because we used a lot of A, H, and K to do graphing on this. When we're trying to find intercepts, like our ratio of our constants, we're going to use this for how we do asymptotes, looking at discontinuities. It's a lot easier if we have it in quotient form because it's then just one type of way of doing it to remember instead of two entirely different techniques to do the same thing. So if we switch this into quotient form, I can use all the same techniques. And so if I want to make this be one single fraction instead of two separate terms, I'm going to need to be able to combine some things together here. In order to be able to combine two pieces together when one of them has a denominator, what does this one need to have? The same denominator, right? we would need them to have common denominators to be able to combine them together. So if I need this piece, this 2, to have a common denominator with this fraction over here, what do I need to multiply this by? A funny looking 1. I want them to have a common denominator, so I would really like this 2 to have a denominator of x plus 3, so I can smush them together. But I can't just multiply it by x plus 3 in the denominator randomly. However, I can multiply it by a funny looking 1. That's going to give us our 4 over x plus 3 minus, and I'm going to multiply this up, my 2x plus 2 times 3 is 6. Now that they have that common denominator, we can smush them together. And we need to be super careful because we are subtracting here. What is 4 minus 2 plus 6? What do we get when we simplify the numerators? Careful, careful, careful. Negative 2x. I have nothing minus 2x. 0 minus 2. Negative 2x. 4 minus 6. Negative 2. So we have negative 2x minus 2. This is 100% the same exact thing as our original function. 4 over x plus 3 minus 2 is exactly the same thing as negative 2x minus 2 over x plus 3. And now that it's in quotient form, we can find our x-intercepts. I could find my y-intercepts. I could go back and find my domain. I could combine these all together. So for our x-intercept, that's our zeros of our numerator. So negative 2x minus 2 equals 0. What is our x-intercept going to be? It is going to be negative 1. So we're going to add 2 to both sides. Divide by negative 2, and we get x equals negative 1 as our x-intercept. So negative 1, 0 is our only x-intercept for this function. That's our x-intercept. For our y-intercept, that's when we're looking for our ratio of our constants. What are our constants? Negative 2 and 3. So our y-intercept is going to be the point 0, negative 2 over 3. And we don't have to substitute anything in at all because those are our guys. So our y-intercept is at 0, negative 2/3. So putting it into quotient form takes a little bit longer at the beginning, but it's going to make a lot of our other calculations a lot easier. You can absolutely do it in its transformation form to find our y-intercept. We would still substitute in 0 for x. To find our x-intercept, we'd have to sub in 0 for y and solve for x. Doable, totally fine, just a bit more calculation. So it's just 6 1/2 a dozen of another. Questions on this one? Say that again? Oh, we have a lot more pieces to go. Rational functions have so many pieces. Because we have domain, we had our intercepts, x-intercepts, y-intercepts. We're going to have discontinuities are going to make a comeback. And we have to then deal with asymptotes. So, questions on this page? There we go.
so random.
So we're also going to have removable discontinuities again. These are our holes. Looks like somebody stabbed the line. So we'll see these in like equations, and that's when we have like these guys. We saw these when we were looking at our limits and all that other kind of stuff. Those pieces, this is where they're coming from. So we're going to be looking at removable discontinuities. And what that is when I have the exact same factor in the numerator and in the denominator. So in order to find out if we even have a discontinuity, we're going to have to factor the numerator and the denominator. So again, this is going to be something we're going to do in its quotient form. More often than not, we're going to be given problems in quotient form because that is the way we do most things with these. So in order to find out if we even have a discontinuity, we're going to need to factor both of these. We're going to factor our x squared minus 6x plus 8, that numerator. And we're going to factor our x squared plus 4x minus 12, our denominator. And again, I don't care how you factor, just that you factor. So if we're looking at this numerator here, x squared minus 6x plus 8. We need a pair of numbers, multiplies to be 8, adds to be negative 6. Negative 4 and negative 2. So our factored form on this is going to be our x minus 4 and our x minus 2. Factor. We're going to do the same thing with our denominator. We're going to try and factor this guy as much as we can. So we're going to find a pair of numbers that multiplies to be negative 12, adds to be positive 4. 6 and negative 2. So we're going to have our x with a positive 6, x with a negative 2. And we have a piece that cancels out. If we have a chunk that cancels out, that's where we have a discontinuity. So we have this piece in both our numerator and our denominator. This x minus 2 is going to wind up canceling out. This x minus 2 is where our discontinuity is located. So to figure out its location, we set it equal to 0. That's going to give us where our x value has a problem. So what is the x value of our discontinuity? 2. Discontinuities are points. So we know the x value of our point. To get the y value of our point, what we're going to do is we're going to take our function, but we have to do it after we've taken out this 2. Because if I plug in 2 right here, I'm going to get undefined. So we're going to take anything we had that was left over. So we're going to be left with our x minus 4 over x plus 6. That's what this simplifies down to. That is what our line is going to look like everywhere else. So to get the value for our y, for our discontinuity, we're going to substitute that in. So we're going to take our 2 minus 4 over our 2 plus 6. So we're substituting in our discontinuity into what's left over. What do we get when we simplify 2 minus 4 over 2 plus 6? Yes, because we're going to wind up with negative 2 over 8, which simplifies down to be negative 1/4. So our discontinuity, when we're plotting this up, is going to be the point to negative 1/4. Discontinuities, like these, like holes up here, they are points. It's in a line, it's written as a point, it's just an open circle. So it should be written as a point. So we cancel it out, substitute it back into the leftover bits. question on our discontinuities. Anybody need more time on this page? Okay. Our last kind of category that we're working with are going to be our asymptotes. We have two kinds of asymptotes that we're going to look at. The first one we're going to deal with is the one we've seen a lot of when we dealt with rational functions, our vertical asymptotes. And in fact, we've already kind of found them. We just didn't talk about it when we did. Oh, what? Because our vertical asymptotes happen when our denominator equals 0. So I could just factor my denominator. The only problem is I'm not going to have an asymptote where there is a hole or a removable discontinuity. So I need to factor both numerator and denominator to make sure we don't have a discontinuity first. So asymptotes are where we have the denominator equal to 0, except for where there's a hole. So in order to see where our vertical asymptotes are, we are going to have to factor both numerator and denominator. We are going to be factoring out the wazoo for section 4.5 and 4.6, I think. So again, I don't care how you factor, just that you factor. When we have an A value like this 4 out front, please be double extra careful. I have a lot of us that keep forgetting about those A values out in front, and it makes our factors wrong, so do not forget that. Your factors are not x plus 7 and x minus 4. So factor this guy however you want, and then factor our denominator as well. So our numbers that we are using a -4 and a +7 to get our numbers that multiply to make a -28 and add to make 3. You just got to be careful whether you're using split the middle, bottoms up, whatever technique you use to get our factors, because what is the factored form of our numerator? X minus 1 and 4x plus 7. It is very important that we factor correctly. If you do not have a reliable way to factor, that is your job this weekend, is to go onto YouTube and figure out which method of factoring works for you and your brain. We need to be able to factor reliably. There are lots of techniques for factoring. We've got the box, we've got the area model, split the middle, bottoms up, grouping. I'm sure there's more. Those are the only ones that come to the top of mind. But there's lots of options. We need to be able to factor. We need to be able to factor. We need to be able to factor. So factoring the denominator, very, very similar. Multiplying to be 15, adding to be 8. That one's x plus 5 and x plus 3. When we don't have an A value, we are usually much better at that. It's that A value that throws us off, that 4 in front that throws us off. So when we get this into factored form, we can see this does not have any discontinuities. We do not have any holes in here. I do not have the same factored numerator and denominator. So only thing we have is asymptotes in our denominator. If we had a discontinuity, it wouldn't count towards asymptotes. Anything that's in the denominator causes an asymptote for us when it equals 0. So just like we did when we were finding our domain, we want to figure out where x plus 5 equals 0, and we want to know when x plus 3 equals 0. So we're usually pretty good at finding these roots. -5, and -3. These are the values that we exclude from our domain as well. They're the ones that cause us problems. Same thing with the removable discontinuities. That's what causes us problems in our domain. When we don't have a removable discontinuity, these are our asymptotes. So we don't need to substitute anything back in because they're not points. These are lines. These are the asymptotes, just written exactly like this. X equals -5 is a vertical line at -5. So like when we get to the point of graphing these, that would be that we have an asymptote like this at -5. And we'd have another one at -3. So when we have asymptotes, they are written as lines. When we have discontinuities, they're written as points because it's just a point. So we write our lines as lines, x equals, we write our points as points, parentheses, ordered pair. We have one last category. And it's still an asymptote. Because we've had our vertical asymptotes. Now we need to know what's happening in the other direction. Because this is where we're going to have a couple of kinds of asymptotes. So in Algebra 2, mostly we saw having x squareds over x squareds. Or we might have had a number over x or not, like x over x squared. We're going to see all kinds of different functions for our chapter. So let me capture that. Anybody need more time on this one? Because there's going to be a bunch of words. So we are looking at what we call the end behavior asymptotes. What that just means is whether we have a horizontal asymptote, or may have done this in honors, but I know in regular we didn't, to do a slant asymptote. And this is based off of our quotient form. So this is only looking at quotient form right here. And the way we know whether we have horizontal or slant is we look at our degree. So the degree of our numerator versus the degree of our denominator. So in quotient form, that's what we mean by down here with the no constant added bit. That's talking about quotient form. So if our degree of the numerator is smaller than the degree of our denominator, meaning we have like x over x squared, degree of 1 over degree 2, degree of the numerator being smaller. That means we have an asymptote at y equals 0. I'll show you why when we go through an example with them, I promise. When we're looking at exactly equal, so x squared over x squared, they both have degree 2. What we'll do is we'll take the ratio of our leading coefficients, like how we did our ratio of our constants. We're going to do ratio of the leading coefficients. So if I had x squared over 2x squared, leading coefficient of 1, leading coefficient of 2. 1/2 would be where our asymptote is. Ratio of the leading coefficients. And again, we're going to practice it. The tricksy one is the top heavy. When I have a higher degree on the top than I have on the bottom. X squared over x. What we're going to have to do when we have something with a higher degree on the top than the denominator is we're going to have to do division. Long division or synthetic, either way. But that's going to give us a usually linear equation left over. And that, y equals mx plus b, will be our asymptote. And we are going to practice with all... No, go away. Someone's taking over my iPad. Go away. Okay. There we go. I don't like that. I don't want it to take over my iPad. So we're going to work with all of these. This is our last bit of things we need before we'll start working with these tomorrow and graphing. We're going to have to graph these suckers. I know. We're going to practice. I promise. And I got a lot of pens still going, so I'm gonna let you guys keep rocking with it. There's a lot of things on here. The hardest part with these rational functions is just the sheer amount of things. The calculations themselves are usually not awful. It's that we have x-intercepts and y-intercepts and vertical asymptotes and horizontal asymptotes and all kinds of things. So many different things. It's like juggling. The movement itself is not challenging. It is the number of things you're catching that's harder. I can juggle with one thing, no problem. Juggling with 6, no. So the hard part is all the things. Still have a bunch of pencils going. Anyone need more time on this page? Woo. Okay. We're not going to do this one on the right. There we go. So we're going to take a look at some examples of our kinds of asymptotes that we're looking at here. So this first one we're looking at, I have 3x squared plus 5x minus 4 over 4x squared minus 2x plus 1. And what I notice, first of all, is that we have degree 2 over degree 2. I have equal degree. When we have an equal degree, we're looking at our ratio of the leading coefficients. So what is the leading coefficient of my numerator? 3. Whoa, chunky pen. What is the ratio of my denominator? Or, sorry, the leading coefficient of my denominator is 4. So this ratio, 3/4, this is my asymptote. We're going to have a horizontal asymptote at y equals 3/4. That's our asymptote. If we get one in transformation form, we're going to switch it back here to get the ratio of our leading coefficients. So just like we did on the very, like that second one we did where we multiplied by the common denominator to make it back together, just like that. Okay? There we go. So we're going to look at this next one. Again, we're just going to do the one on the right. I just can't pre-erase things because my computer's in a mood. But I'd rather us see stuff than to talk through. So when we have one like this one, where we've got f of x equals x plus 3 over x squared plus 4x minus 2. We're given this function here. We have, in our numerator, our degree is 1. In our denominator, our degree is 2. So we definitely have a higher degree in the denominator. So you can either, remember, if we have a higher degree in the denominator, it's always going to be at y equals 0. There, you can use equal to be exactly the same kind of concept. So where we'd have our ratio of our leading coefficients, as long as we remember that this has 0 x squareds. Then that would give us that ratio of our leading coefficients of 0 over 1, which is exactly the same thing as y equals 0. So you can put equal and bottom heavy into that same kind of category as long as, remember, we have to use the same term, that biggest term. So we'll have a 0 over 1, or we'll have 2 over 1, or we'll have 1 over 2, whatever that ratio of our leading coefficients is. That'll even help a little bit if we have the top heavy where I have a higher degree on the top than on the bottom, because I get a number over 0, and that means we'll have to divide. So this gives us our horizontal asymptote here at y equals 0. Whenever we have a higher degree in the denominator, it's going to wind up being 0 every single time. The last option we're going to have is when we have something that has that higher power on the top, lower power in the denominator. What we're going to do is we're going to divide. We will practice with that tomorrow because we have 2 minutes to the end of the period, and I'm not going to have us try and speed run that.
Bottom heavy is always going to be y equals 0.
Bottom heavy is always going to be y equals 0. Every time. So I was like, if you want to remember just that phrase, totally fine. If you want to do the leading coefficients, also works. Yes. All right. So. Oh, hang on. Let me capture that. Okay. Then I can do that.
Yeah, gap junctions are also